Hello everyone, we are now in our week 3, lesson 3. Last time, we discussed the balanced and unbalanced forces. We learned that the object with balanced force is at rest with zero net force, while forces under unbalanced forces may stop, start motion, change direction, slow down, or speed up depending on the non-zero force that acts on them. Today, class, we will learn the following competencies. Our enabling competencies, number 1, infer that circular motion requires the application of constant force directed toward the center of the circle. Number 2, differentiate potential energy and kinetic energy. Our most essential learning competency for this week, we are going to identify and explain the factors that affect potential and kinetic energy. Let us start our discussion by defining what is energy. Energy is defined as the ability to do work. Work is an abstract idea related to energy. When work is done, it is accompanied by a change in a motion. When work is done by an object, it loses energy. On the other hand, when work is done on an object, the object gains energy. Have you ever experienced riding in a roller coaster? Today, let us try our 2D dimensions of riding a roller coaster. Are you ready?
Here we go! Alright, now that's a crazy lift hill right off the side of the mountain. Ocean Park is known for its amazing views from the top of the coasters, and that does not disappoint at all. All right, here we go. Woo! Whoa! Whee! Oh, man! Woo! Airtime hill! Awesome airtime hill! Another amazing view.
In a roller coaster, energy changes from potential to kinetic energy, and back again many times over the course of a ride. All moving objects possess kinetic energy, which is determined by the mass and the speed of the object. Potential energy is the energy an object has as a result of its position. As we have said, potential energy, the energy possessed by a body by virtue of its position relative to others, stresses within itself, electric charge, and other factors. Potential energy is present when the work is waiting to be done, or when there is a potential for work to be performed. It is affected by the mass of the object and the gravitational force. This is an illustration where a man lifting a box to be placed in the table. Which or who is doing work in this illustration? Is it the man, the box, or the table? Yes, you are correct. If you answer the man is doing the work on the box, what is the direction of the force of the man exerted on the box? Yes, it is upward. What is the direction of the motion of the box? Upward as well. Then, we can say work is done by the man on the box. When an object is lifted from the ground, the work done is against the force of gravity. An object gains energy when raised from the ground and lose energy when to fall made, or when made to fall. The energy is gained or lost by the object is called gravitational potential energy, or simply potential energy. The mass and the position greatly affects potential energy. The two objects that are in the same position have potential energy. Yet, an object with greater mass has a greater potential energy with respect to its position. An object of the same mass that is placed at different positions have different potential energy contained. The object with higher position has greater potential energy. The equation for potential energy is potential energy is equal to m times g times h, or mgh, where m is the mass, g for acceleration due to gravity, which is constant, and h for the height. Please take note that the acceleration due to gravity is always equal to 9.8 meter per second square. Let us have this problem number 1. Following the Gressa method. If 1 kilogram book is lifted on a table with a height of 2 meters, what is the potential energy of the book? Given numbers. Mass is equal to 1 kilogram. Height is equal to 2 meters. And acceleration due to gravity is equal to 9.8 meter per second square. Required potential energy. Equation. Potential energy is equal to mass times gravity times height. Solution. Potential energy is equal to 1 kilogram times 9.8 meter per second square times 2 meters. And the answer is potential energy is equal to 19.6 joules. Joule is the unit used for energy. Example number 2. A box has a mass of 5.8 kilogram. The box lifted from the garage floor and placed on a shelf. If the box gains 145 joules of potential energy, how high is the shelf? A box. So here are the given numbers. For the mass, 5.8 kilograms. Potential energy, 145 joules. And acceleration due to gravity, that is equal to 9.8 meter per second square. Required height. Equation. Height is equal to potential energy divided by mass times gravity. Solution. Height is equal to 145 joules divided by 5.8 kilograms times 9.8 meter per second square. Answer. Height is equal to 202.55 meter. The gravitational potential energy is just one type of potential energy. Another type of elastic potential energy is the elastic potential energy. Springs and rubber bands are called elastic. When elastic are stretched and then let go, they will return to the original form if they were not stretched beyond their elastic limits. Consider the bow and arrow. Since the force exerted in stretching the bow causes the change in length, then work is done on the bow. When work is done, energy is transferred. Thus, the stretched bow gains potential energy. The elastic potential energy depends on how much the elastic object is stretched or compressed and the elasticity of the material. Let us go now to the second type of energy, the kinetic energy, energy of moving objects. The energy of the moving objects is called kinetic energy or energy of motion. The word kinetic comes from the Greek word kinetikos, which means moving. Kinetic energy quantifies the amount of work the object can do because of its motion. Look at this illustration. Potential energy is always connected with kinetic energy. When this child stretches this slingshot, the elastic potential energy of the rubber increases. When he releases the slingshot, the stored energy or potential energy will be converted into moving or kinetic energy. Let us now have the mathematical equation of kinetic energy. Kinetic energy is equal to 1/2 mv squared. M is equal to mass and V is equal to velocity. Mass and velocity, or the kinetic energy, depends on the mass and velocity. From the equation, you see that kinetic energy depends on its mass and velocity. What will happen to the kinetic energy of an object when the mass is doubled, but the velocity will remain the same? How much when the velocity is doubled and the mass remains the same? In order to answer those questions, let us answer the sample problem of kinetic energy. Here is another sample problem. A 1,000 kilogram car has velocity of 17 meter per second. What is the car's kinetic energy? Given, mass is equal to 1,000 kilogram. Velocity, 17 meter per second. Required, kinetic energy. Equation, kinetic energy is equal to 1/2 mv squared. Solution. Kinetic energy is equal to 1/2 of 1,000 kilogram multiplied by 17 meter per second square. The answer is kinetic energy is equal to 144,500 joules. Again, another sample problem number 2. A cyclist and bike have a total mass of 100 kg and a speed of 15 meter per second. Calculate the kinetic energy. Given, mass is equal to 100 kg. Velocity is equal to 15 meter per second. Required kinetic energy. Equation. Kinetic energy is equal to 1/2 mv squared. Solution. Kinetic energy is equal to 1/2 of 100 kg multiplied by 15 meter per second square. Answer. Kinetic energy is equal to 11,250 joules. That's all. Thank you for joining class today. You can now go to our classroom for you to have our activity number 2 regarding our lesson. And after that, you may now answer your learning task for the week. Thank you.